All right, and we're back. Last time we looked at problems that just really had to deal with the force of gravity and also some tougher questions along with that. Now we're going to get into what I think is going to start being a little bit of fun because create is probably not the best word, but we get to start mixing and matching a few equations. Fairly simple equations that you've seen before, but we get to start seeing how they work together to produce some interesting results. And number one on that is determining acceleration due to gravity. I've always just told you that the acceleration due to gravity on Earth is, let's say, 10 meters per second squared, or in Regents last year you were told what the acceleration due to gravity is on other locations. It turns out that there is actually an equation for determining the the acceleration due to gravity, and we can determine that equation by doing just a very little bit of very simple algebra. So let's look at this first question. What is the acceleration due to gravity near the surface of Mars, which has a radius of 3.39 times 10 to the 6th meters and a mass of 6.41 times 10 to the 23rd kilograms? So I suppose we could do this in two steps. We could, I guess what we could do is think of like a hypothetical object, maybe like a 10 kilogram object, figure out what its weight is on Mars, and then use Fg equals mg to find what g is. But that's really kind of involved, okay? That's a lot of calculation for not a lot of gain. Instead, what I'm going to do is we're going to combine the two equations that we know for the force of gravity. We know that the force of gravity is Fg equals mg. This is used for local cases when we don't have very big objects, typically, but you can use it if you know what g is, which is what we're kind of determining. We also know what the force of gravity, Newton's universal law of gravitation equation is. And we know that that is g times m1 and m2, although in this case I'm going to use little m and big M over r squared. The two different equations for the force of gravity must be equal to each other. It wouldn't make sense if one equation gave one answer and one gave the other. Now, you'll notice here that something will cancel out. Remember so this m right here is the mass of the object you want to know the weight of. Usually it's the little object. It's the object that's resting on the surface of the bigger object, like Earth or the Moon, or Mars in this case. Well, that object also shows up over here with the little m right here. Big M is the mass of the overall of the big object. Little m is the mass of the little object. So if I have little m here and little m here, they will cancel out. And what this leaves me with is an equation that says g, little g, acceleration due to gravity, is equal to uppercase g, the universal gravitational constant, multiplied by the mass of the big body that the object is on, that we want to know the acceleration due to gravity for, divided by r squared, where r is the distance between the two objects. Now, one of those objects is canceled out, but we know that the two objects were the object on the surface and the actual big object that the object is on, such as Earth, Moon, Mars. Now, what is that r? Well, if it's on the surface, near the surface of Mars, that essentially means that the distance between the object and the planet or moon or whatever it may be is just the radius. So what this equation shows us is that we can calculate the acceleration due to gravity if we know the mass of the planet or moon, and we also know the radius of the planet or moon. We can calculate the acceleration due to gravity near that body's surface. Now, can we just skip right to this equation? No, I would caution against that. But it is fairly easy to derive. It's 1, 2, maybe 3 steps. So now, if we go to calculate g for Mars, big G is 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. The mass of Mars is 6.41, as we were told, times 10 to the 23rd kilograms. And the radius of Mars, which don't forget is squared, we haven't canceled that out, 3.39 times 10 to the 6th meters. I can calculate that for us right now. 6.67 e negative 11 times 6.41 e to the 23rd divided by 3.39 e6. Oh I should have squared that first. Okay, yes, it still worked out okay. I almost mistyped something in the calculator. We get g is equal to approximately 3.7 meters per second squared. If you don't believe me, go online, look it up. That is what they will say the acceleration due to gravity for Mars is. We can do the same thing for Neptune. Even though Neptune doesn't really have a surface, we can pretend that the outer layer of clouds is its surface. What's the acceleration due to gravity near the cloud surface of Neptune? It has a mass of 1.02 times 10 to the 26 kilograms and a radius of 2.46 times 10 to the 7th meters. Well, again, like I said, we're not going to skip right to this equation. We're going to show how we get it. We know Fg equals mg. We also know that Fg equals g little m big M over r squared. The little m's cancel out. And look at that, acceleration due to gravity, by the way, this is interesting. The acceleration due to gravity is only dependent on the properties of the big body that the other object is on, so the Earth, the Moon, Mars. If you remember, this just goes to show why all objects accelerate at the same rate. It has nothing to do with their mass. Their mass cancels out. All it has to do with is the mass of the body on which they are, the body which they're on, and how big in size that body is, what the radius of that body is. Very interesting. So we're left with g equals gm over r squared. For Neptune, well, universal gravitational constant is still the same thing, 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. Neptune's mass, 1.02 times 10 to the 26 kilograms. And the radius, 2.46 times 10 to the 7th meters. Okay, we see the acceleration due to gravity on Neptune is a little bit more than ours, actually. And again, that's just at the outer layer of Neptune's clouds. Neptune is one of those gas giants, so this, I think it would get bigger as it goes in. I don't know the composition of Neptune, so I don't know the density profile. But anyways, at the surface, Neptune's acceleration due to gravity is bigger. Even though it's much bigger radius than Earth, its mass is so much bigger that it more than makes up for that. Okay, moving on. A new planet is discovered with a mass that is 4 times as big as Earth's mass and a radius that is 3 times as big. What is the gravitational field strength at the planet's surface? Remember, gravitational field strength just means what is g? What is the acceleration due to gravity? Once again, and I really recommend writing these this derivation down just so you get used to the idea of why you're doing it. Gmm over r squared, mg, cancel the m's. G equals g m over r squared. So let's say that this is for Earth. Okay? We want to know the gravitational field strength somewhere else. And that somewhere else includes a mass that is 4 times as big as Earth's. So we're going to label that as 4m. And a radius that's 3 times as big. So that would be 3r. And that whole thing gets squared. So we're going to do a little bit of math here. That 4 can come out to the front. 4gm. 3r, whole thing squared, would be 9r squared. You look right here, gm over r squared is the same thing as the g for Earth. And as we know, g for Earth is 10. If we do 4/9 times 10 meters per second squared, we get 4.44 meters per second squared equals g prime. Okay, so this planet was more massive, but it also was much bigger in size, in physical size, than Earth. So we see that the gravitational acceleration is actually about half as much because it was so much bigger in size. What is the gravitational field strength 3 planetary radii away from the planet's center? I always recommend drawing these out. Let's say here's the planet. Here's 1 radius. 2. That's 3 radii from the center. Okay? Before the planet was here, or the object was, we were looking at something at the surface. Now we're looking 3 radii away from the center. So that means g double prime is going to be g, still 4m. Okay. Oh, by the way, since this is the same problem, we'll just go right to our equation. G 4m, And in this case, remember, this R prime here, R double prime is 3 R primes. It's 3 planetary radii. But that planetary radii itself was 3 times as much as Earth's. So that's 3 times 3R, which is 9R. So our radius here, our distance between the object up here that we wanted, the object that's at the location where we want to know the gravitational field strength, and down here, that's actually 9 Earth radii. So we're going to put 9R squared. So we get 4 GM over 81 R squared. 4 over 81 times original G is our G prime. And since 481 times 10 meters per second is 0.494 meters per second squared, that is the acceleration due to gravity. 3 planetary radii away from that planet's center. Okay, very, very small. Notice that as we go away from the center of the planet, G decreases. Okay, its objects don't accelerate at the same rate. Okay, we're going to go to something new now. It's called gravitational potential energy. And you might be saying, wait, we know this. It's MGH. For very big objects, like we're talking objects out in space, we don't use MGH. Okay, we use this equation. U, standing for gravitational potential energy, G equals negative G little m big M over R. And what this does is it tells, we want to talk about gravitational potential energy because it tells us how, I'll put in quotes, bound an object is to whatever it's orbiting. Okay, we use this for things like the moon going around the Earth. We use this for satellites in orbit around a planet. We use this for planets in orbit around the sun. All those objects are in bound orbits. They don't just go wherever they want. They are gravitationally bound to stay near whatever they are orbiting. So a couple features here. You notice that it's negative. So gravitational potential energy is always going to be negative here. Okay? And you notice that as R gets really, really big, what happens here? If R gets big, this goes down towards 0. So the reason that this happens, the reason that we have this as being negative, is so that at infinity, if you have something that's an infinitely far distance away, there is 0 potential energy. That's why we don't use MGH. You wouldn't really want to say that saying that things have infinite energy is very, very strange, okay? Negative infinity is actually fine, but infinite energy, that doesn't quite work out. It's like, where did it get the energy from? Remember, conservation of energy says the total amount of energy in the universe is a constant value. So you can't really have something with infinite energy. It doesn't work like that. Basically, if you have something that's an infinitely far distance away, its gravitational potential energy is 0. It's not really bound to that object. As you get closer and closer, the gravitational potential energy becomes more and more negative. All that signifies is that it's more and more bound, and you would need more and more kinetic energy to make the object be truly free. You would need more kinetic energy to allow the object to go wherever it wants and not have to orbit another object. So let's do a calculation with this real quick. A planet with a mass, and we're going to come back to this in another video. A planet with a mass of 9 times 10 to the 26 kilograms orbits a star with a mass of 4.1 times 10 to the 29th kilograms at a distance of 7.2 times 10 to the 10th meters. What's the gravitational potential energy of the system? Notice that you have to have 2 objects for gravitational potential energy. So this is a very straightforward calculation. Negative G little m big M over R. Negative 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. The planet has a mass of 9 times 10 to the 26th kilograms. The star, so planet's smaller than a star, so I'm going to use that as little m. Star has a mass of 4.1 times 10 to the 29th kilograms. And they are 7.2 times 10 to the 10th meters away from each other. We type all this in. We get that the gravitational potential energy is negative 3.42 times 10 to the 35th joules. One more note about that negative, don't get freaked out by it. Remember, we can set the 0 point for gravitational potential energy to be wherever you want, so it's convenient for us, okay? It's very nice like that, okay? So this shows that that planet is very, very bound to its star. Matter of fact, we would need to know how much kinetic energy it has to know if it truly is bound, if it will stay in its orbit forever, or if at some point it goes off into space and never comes back. What would happen to the planet? What would happen if the planet orbited closer to the star? What if it orbited farther away? What if it was infinitely farther away? Well, we can do this by just kind of looking at the equation. If it was closer, r would be smaller. That would mean, essentially, that you would have a bigger negative number. A more negative UG. What that means is it's more bound. It would need even more kinetic energy to escape from its star. If it was farther away, if r was bigger, in a sense, then you would have something that is less bound, because you'd have a less negative UG. It's not as tightly bound to its star. If, in the last case, it's infinitely farther away, in that case, well, UG is 0, and we say that it's unbound. Okay? It's not gravitationally bound to that star. It can go wherever it wants. Okay? When we come back, we'll talk about orbital speed, which is one of my favorites.